Calibration is a process of turning these predicted probabilities into actual probabilities, where we can then say, and we can talk about them as probabilities, where given basically infinite but large enough sample size in practice, we can then say that the expected fraction of positives that we want to observe is going to be equal to the predicted probability of these data points. So if we get 1,000 data points that have predicted probability of 0.9, if that is a real probability, we can expect 900 of them to turn out to be positive. And of course, this expectation is going to match reality more and more as we increase our sample size. That's why aggregating with enough data points is so essential. But let's come back to the problem at hand, and the problem is that we don't have real probabilities. What I plot, actually not what scikit-learn plotted here are person that made scikit-learn docs, which are basically, by the way, amazing when it comes to calibration. What they plotted here is the mean predicted probability of a bucket, where we basically take the our predictions on the test set and we put them in buckets that correspond to let's say we put them in 10 buckets that correspond to specific mean predicted probabilities. So this bucket has mean predicted probability of 0.05, and all the predictions between 0 and let's say 0.01 go in that bucket, etc., etc. That's how we construct the x-axis here. And then for each of those buckets, we're going to compute on the test set the actual fraction of positives that we observe, that we see on that test set. And if the model was well calibrated, what we would expect is a straight line. Basically, what we'd like to see is that the actual mean predicted probability of the bucket corresponds to actual fraction of positives. But as you can see here, with basically all machine learning models, also including neural networks of all kinds, whether transformers, CNNs, or anything else you want with skip connections or without skip connections, we will get very strongly miscalibrated models. There is one exception. That exception is logistic regression. Even here, you see that it's not perfectly calibrated. It actually should be calibrated in expectation. So if you, for some reason, mostly regulation reason, use logistic regression to do your job, then probably you don't need to calibrate your models. Now, let's figure out how we can actually calibrate those models. So what we want to do is we want to take that line that we observed, the calibration curve, and we want to turn it into a perfect calibration curve, which is a straight line. The way we do it is we're going to fit in one-dimensional regression. Generally speaking, there's 3 kinds of models that are used there. It's either sigmoidal regression. As you can see here, some curves really look like sigmoid, so we can assume that the distribution is sigmoidal, and we can fit sigmoidal regression. We can fit isotonic regression, which assumes that if x increases, y cannot go down. So it has this baked-in assumption of isotonicity. Or we can just use a gradient boosted model. And what we're going to do is we're going to basically map the current point in that curve to a point where we would see the actual. So we're going to adjust the classifier's predicted probability so that it matches the fraction of positives. The way we do it is we're going to just, for every point, try to predict the class given the classifier's predicted probability. And then we get something that is reasonably close to a straight line, of course, making sure we don't overfit that calibrating.